Achievers welcomes you. Our topic is syntax and semantics of K. Let's proceed with our presentation. Syntax versus semantics. Basic idea. Syntax. Syntax refers to the formal rules governing the structure and composition of expressions or formulas in a given logic. In model logic, syntax concerns the rules for constructing valid formulas using symbols, operators, and variables. Semantics. Semantics, on the other hand, deals with meaning or interpretation of formulas within a logic. In model logic, semantics provides a framework for understanding how different model operators and formulas relate to the truth values in various possible worlds. Syntax of K. K is one of the basic model logics and it primarily deals with the syntax and semantics of model operators. Model logics are used to reason about necessity and possibility, and K is a foundational system for model logic. Let's break down syntax of K. Propositional variables, atoms. These represent basic statements and are usually denoted by lowercase letters such as P, Q, R. Model operators. First is necessity operator or box operator. This operator is used to express that a particular proposition is necessarily true. It is a unary operator and you can write it as box A, where A is a formula. Possibility operator represented by the diamond shape. This operator is used to express that a particular proposition is possibly true. Like box, it is a unary operator. You can also write it as diamond A, where A is a formula. Logical connectives. K model logics also typically include standard logical connectives such as and, or, not, implies, etc. for building complex formulas. Formula formation rules. Formulas in K are formed according to standard rules of propositional logic with the addition of model operators.
The logic K is an extension of propositional logic. It has two or more connectives, box for necessity and diamond for possibility. The alphabet of the language of K consists of all propositional variables P0, P1, etc., unary connectives, negation, box, diamond, binary connectives, conjunction, disjunctions, implies, if and only if, propositional constant, truth, false, and punctuation marks. The propositional constant, truth, false, and the propositional variables together are called atomic model propositions or atomic model formulas. Now we will look at some examples. P, a basic proposition such as it is raining. Then box P, the necessity of it is raining, meaning it is necessarily true that it is raining. Diamond P, the possibility of the sun is shining, meaning it is possible that the sun is shining. Box P intersection Q, the necessity of the conjunction of it is raining and the sun is shining. Box P implies diamond Q, a complex formula expressing if it is necessarily true that it is raining, then it is possible that the sun is shining. As in propositional logic, one may choose a shorter list of connectives and propositional constant or a longer list including all the binary truth functions such as upper arrow, down arrow, etc. Model propositions are defined recursively by the following formation rules. Each atomic model preposition is a model preposition. If X is a model preposition, then negation of X, box of X, diamond of X are model prepositions. If and X and Y are model prepositions, then so are X disjunction Y, X conjunction Y, X implies Y, X if and only if Y. Each model proposition is generated by applying recursively one or more of the rules from 1 to 3. Using the symbol P as a variable ranging over P of I for all I belongs to natural number. The grammar of model prepositions written generally as Z below in the Baker-Snur form, also known as BNF, can be given as Z is defined as truth, false, P, negation Z, box Z, diamond Z, Z intersection Z, or Z conjunction Z, Z disjunction Z, Z implies Z, or Z biconditional Z.
Unique parsing in K. If Z is a model proposition, then Z is in exactly one of the following forms. That can be true, false, P, negation X, necessity X, possibility of X and Y, X or Y, X implies Y, and X biconditional Y. For unique propositional variable P and unique model proposition X and Y, this can be the parse tree, which is shown in the diagram, and the parse tree for the model proposition is bifurcated in this way.
Semantics and Kripke structures. The semantics of modal logic is often defined in terms of Kripke structures. A Kripke structure is a tuple of W, R, and V, where W is a set of possible worlds, R has an accessibility relation on the set of possible worlds, RWV means the world V is accessible from world W. This relation can be reflexive, transitive, and symmetric, but it can have different properties in other modal logics. And V is an evaluation function that assigns truth values to propositions in each possible world. A model M is basic modal logic is specified by three things: a set W, whose elements are called worlds, a set R, a relation R on W called the accessibility relation, and a function L called the labeling function. Interpretation of modal operators. As we can see, the first operator is true in a world W if and only if A is true in all worlds accessible from W, according to relation R. The second operator is true in a world W if and only if A is true in at least one world accessible from W, according to relation R. And we can see a few examples.
Concept of satisfaction. In modal logic, the semantics of satisfaction and truth are essential concepts when evaluating formulas within a Kripke structure. Let's delve deeper into the satisfaction and truth semantics of the K-model logic. Satisfaction. Satisfaction is a Kripke structure. A formula is considered satisfied in a specific word of a Kripke structure if, when interpreted according to the semantics of the modal logic, it evaluates to true in that word. This means that the formula holds in that word based on the given Kripke structure, accessibility relation, and valuation function. Formula satisfaction. A formula phi is satisfied in a word W of a Kripke structure if and only if, after interpreting all the modal operators, the logical connectivities within phi, it evaluates to true in the world W according to the validation function V for that world.
Our presentation ends here. Thank you.